let's look at how atomic number affects size. All right, it depends on whether you're going across a row and comparing things with the same number of shells, or whether you're going down a group, in which case things have different numbers of shells. Okay, so if I take a look at the shells here in lithium and everything in the second row, these are all in the second row, has got two shells. There's a first shell and then a second shell. Okay, and if I look at the next one, it also has two shells, but because it is a +4 charge instead of a +3 charge on the nucleus. And I can tell the charge just by looking at the atomic number, right? The 1s is going to be drawn in. The first shell is going to be drawn in a little bit more. So this one's going to end up a little smaller because the positively charged nucleus is drawing in the negatively charged shells a little bit closer. And if you were to look at boron, it would be even more, it would compact them in a little bit more. So that would be even slightly smaller. So let's summarize that. When you have the same number of shells, larger atomic number gives you a smaller atom. Okay, now when you take a look at sodium, you're going down a column on the periodic table. See, sodium is underneath lithium here, so you're adding an extra shell on. So you would think, because you have got a +11 charge on a sodium, that you would have an even smaller first and second shell, and you're right. But you're adding a third shell on there. Now notice I drew that third shell a little bit bigger. There's a subtle effect going on here. When you have these first two shells sort of wrapped real tight around the nucleus, they screen the charge of the nucleus from the outer shell. So the outer shell tends to go on a little bit bigger than the core shells. The core shells are wrapped around the nucleus really tight, and the valence shell, the outermost shell, tends to be bigger and fluffier. So this ends up bigger. Even though the atomic number is bigger, the atom is bigger. And you could even say, you know, this has a smaller atomic number and it has a smaller atom, which doesn't make sense according to what we saw up here if you don't look closely. But there are two rules. This is one rule. The other rule is more shells, bigger atom. Or you could say fewer shells give you a bigger atom. Now this trend here works inside isoelectronic series. Those are series that have identical electron configurations. They have the same number of shells, so you can compare things in an isoelectronic series just by looking at the atomic number. The thing with the biggest atomic number will be the smallest whenever you have the same number of shells.